Hello, I'd like to welcome you all to this video as a follow-up. This is a follow-up on the lesson that we did on prime width modulation, in which I went into some theories on how we do PWM. You could see that we was trying to demonstrate and trying to explain the concept of prime width modulation and how we can actually code it. And so there was a lot of theory that I talked about, and you may just need to refer to that video to have a continuity in understanding on how prime width modulation goes. Now, I'm not all about that today. Today, I'm just all about explaining how we apply this prime width modulation, how we apply it in the Arduino microcontroller. That's what we're going to look at. So basically, just to keep it simple, here is a scenario. You have, this is your Arduino microcontroller, and then you have one of the ports. What we're going to demonstrate is that we are going to have a potentiometer on one of the ports. And in this potentiometer is going to be connected to port A0. Now I'm going to explain why in this case I'm choosing an analog port to do prime width modulation. And so in this potentiometer, which is connected to the ground, we are going to try to we're going to be reading the analog voltages. Of course, we're going to try to input analog voltages to the potentiometer, but then the A0, we all know from the theory of ADC that we're going to be, the A0 will be spitting back to us the digital value. So it is that digital value that would want to use in our prime width modulation to be able to produce the different duty cycles on port. In this case, we're going to choose port A3. We're going to choose port 3. Right, digital port 3. So on digital port 3, we're going to connect our LED. This LED is one that is going to light depending on the different values of the duty cycle. Now, I just want to mention here, remember that we try to look at the theory behind it. So let me just remind you a few things. So voltage output that goes, in this case, for example, to the LED will be equal to the duty cycle multiplied by the voltage supply. Now, in this case, the voltage supply, definitely this could be the voltage supply that in this case is being received from the is coming from the Arduino, and that's approximately about 5 volts. And now this duty cycle will be a value that ranges, in this case, when we explained about my controllers, that this is a value that may lie between 0 and 255. All right, so this value will be a fraction of any value that lies between 0 and 255 will be multiplied by Vs. Now remember that the duty cycle is actually a percentage, and so when we say that counting starts from 0, we can count from 0, and the overflow value is 255. So what we can even simply say is that any value that lies in the middle of this, like, there are about 256 steps, of course, if we count them, but we can pick any value that lies in the middle, like 127 out of 256, and that times 100%, that could become like a duty cycle that we can use to factor the voltage output. So the voltage output will be, so we mentioned that this could be an OCR over 256, for example, and times 100%, that becomes like the duty cycle. So what we're going to try to do here is that we're going to try to see if we can get the values that are coming from the A0 and then multiply that by the voltage supply. Okay, so let's just try to see what we're going to do about this. Now notice how now this is very interesting. So what we're going to do is we're going to look at the Arduino itself. How does it do PWM? So now from the previous lesson I showed you that if you look at PWM on the Arduino, there are actually specific pins that do that. For example, pin number 3 is one of them, 5, I think 6, 9, I think should be also 11. These pins could actually output a prime width modulated signal. So not every pin is able to do that. So in our setup, we have A0 connected, where we are connecting the potentiometer, and then we have got pin number 3 as one of the pins that could do the PWM. Now, what we mean is that these pins can produce a signal that is doing like this, depending on how you do the configuration. So now real quickly here, I just want to show you, for example, now for us to be able to do the PWM on the Arduino, there is a function, it's called the analog write command, analog write. So now the analog write, what the analog write command does, it takes the value of the duty cycle. So we can say duty cycle, it takes the duty cycle, it takes the duty cycle, that's what it does. It takes the duty cycle, and then that's the import, the duty cycle. And now this duty cycle is a value that lies between 0 and 255. Now it's a fraction of 256. Okay, because there are about 256 steps. So it takes a value that lies between this, and it outputs that value to pin number 3, pin number 5, or pin number 6. And now when you do that, it means that the prime width, what is this prime width? So if this is our period, right? So the relationship between the period and the T on, so the T on over TS, in this case, this is the T on portion times 100%. That is usually our duty cycle. But in this case, in microcontrollers, we can say that this could be any value between 0 and 255. So we can say any value between 0 and 255, let's say 127 over 256, because there are about 256 steps. When we multiply that by 100, that becomes like our duty cycle, right? And so what we are saying in this case, if you look at it, of course, PWM, in this case, we are showing that we can have a switching period of TS. And actually, an Arduino may be output should be about 500 Hz. Now, gotta check that one out. Pins of Arduino can put up to about the maximum of 500 Hz. But the way we are doing it right now is that we're trying to show you that whatever is going to be as a duty cycle and sent to pin 3, the portion is depending on the value that you're actually loading. In this case, if we looked at the Arduino at megathread 2, you could see that that was the output compare register value if you're running it in TCT mode. Now, so the analog write command is the Arduino way of doing prime width modulation. So all you are doing is you're sending values between 0 and 255, and out of the total 256, that it becomes the duty cycle that is sent to pin number 3, pin number 5, pin number 6, or pin number 9. So that's exactly what we're gonna do. Now, there's just one thing I want to show you. So now, having explained that, so let's just try to look at how do we code this. How do we write a code? So I've just shown you here, for example, that we're going to have an analog of the potentiometer connected to port A0, and we're going to have also the digital pin number 3, which is, we know that it's one of the pins that does the PWM. And so we're going to change the different values or different digital valve values. We're going to now try to use those digital valve values to use them as the duty cycle that we can get, such that we make the system sort of dynamic and sort of interactive. that I can determine what duty cycle I'm sending to pin number 3 depending on the value that is actually read from A0. Now, to be able to achieve this functionality, I just want to show you that there's just one more thing that I want you to understand before we go to writing the code. Remember that the ADC, analog to digital conversion, we talked about this. You need to watch one of my videos. We did actually mention that the digital value that is read from the analog pins. So we know that the ADC, analog to digital converters, ports, they have what we call a 10 bits, what we call resolution system, right? We mentioned this, meaning that whatever voltage that is being read from pin A0 or port A0, for example, whatever voltage that is being read, that is coming in, it could be 2.5 volts, for example, right? We did mention that this voltage value is actually converted in values that lie between 0 and 1024. That's actually what we mentioned, right? We mentioned that we could get a 0 to 5 volts, any value that lies between 0 to 5 volts that enters into the A0 port or A1 port or any port that does analog to digital conversion on Arduino, is actually converted to a digital value that lies between 0 and 1024. Right? That's what we mentioned. But there's another thing about PWM. Now, PWM uses the command analog read, analog write. Now, it takes a value which is called a duty cycle, right? And then it outputs it to any of the pins. In this case, I choose pin 3, all the pins that do analog to digital conversion. Now, the challenge that we have right here is that, look, the duty cycle should be a value that lies between 0 and 255. But then the value that we're going to read from the A0, which is the digital value, is a value that lies between 0 and 1024. But then we need a value that lies between 0 and 255 if we have to. So it means that when we are reading from A0, we could read a value that is way beyond 255, and which just doesn't work very correctly for our duty cycle. We may get out of range. And here we are supposed to read between 0 and 1024, and which we are going to do actually when we read from the A0. But then now, for us to be able to use the analog write command, we should be able to make sure that the value that is read between 0 and 1024 does not really go beyond 255. And how can we do that? And so this is what I'm trying to now show you, that there is a command in Arduino, and in this command, it's called the map function. In fact, it's not a command, it's a function. Okay, there is a function, and this function is called the map function. Okay, it's a map function. Now, what does the map function do? So the map function, what it does, it's able to scale any ranges of values that lie between certain values. For example, let me just show you what the map function does. So the map function, it takes a value, let's say this value, it takes a value, then it takes that value and it says this value that lies, let's say, between 0 and 1024, or between 0 and 1023, by the way, it's between 0 and 1020. In this case, we're saying between 0 and 1023 because, of course, though they are about 1024, I mentioned here 1024, right? Just want to make sure that I'm really getting it. Yeah, actually, it's supposed to be between 0 and 1024. So fact, it's supposed to be between 0 and 1023 and not 1024, because if we have got up to about 1023 steps, 1024 steps, okay, let's just get this. 0 and 1023. Where is my pen? Okay, so now we're saying that this value that lies between 0 and 1023 can actually be mapped to a value that lies between 0 and 255. Right, so you can see here that with the map function, we can actually map a value that lies between 0 and 2023 to 0 and 25. So now we've actually found a way. Now, what is this way? This way means that even if I read a value from A0, the digital value, which I'm going to read using a potentiometer, and this value is going to lie between 0 and 1023, because we know that 1024 steps. I've been saying 1024, right? You can just say it's 0 between 0 and 1023, but of course they're about 1024 steps. And even here between 0 and 255, but we know they're about 256 steps. So this value that is read between 0 and 1023 can actually be translated into a value that lies between 0 and 255, and that's what makes it compatible for our PWM. It makes it very compatible. And what a neat feature, what a neat function the map function is in this case, because if we were just to read this value, for example, and then take it directly to the analog write command, it would throw an error, because then the analog write command, the duty cycle part has to lie between 0 and 1025 and 255. So now let's just quickly look at how we can possibly write. So we have a scenario in which we're saying that this is our A0, and this A0 has got the analog port, and then we are saying that we are reading the value, and whatever we are reading the value, we are using it as a duty cycle to the LED right here, right? And so this LED will have to actually light up with different duty cycle values. So it will have a 50% duty cycle, 40% duty cycle, and whatever duty cycle that you want to read. And then what we're going to use the analog write command. And the analog write command will get whatever we have read from the A0, but then mapped between 0 and 255, and then we're going to output that to pin 3. So now real quickly, let me just show you how can we approach the coding. This is what we're going to do in approaching the coding. So the first thing that I want to show you is that we are going to, first of all, let's just say that we're going to say int PWM pin. I call this as a PWM pin. It's going to be pin number 3. We know that. And let's say that we're going to also declare a variable called float. And I'll say float digital val, and I'll just look at that. I'll do that. And then I'll say also int analog pin, and I'll call this as pin 0, right? All right, so that is what we're going to do in terms of the pins. Then I'm also going to call a value called float, and I'll call this float as my duty cycle. And that is it. And so now in the void setup, which is the void setup, what I'm going to do in the void setup, I'm just going to now just maybe make pin, I'm just going to say that I'm just going to say pin mode. The pin mode, what is the pin mode? Pin mode PWM pin. I'm just going to make it as an output pin, output. Now in this case, there is actually no need for us to even make it as a, it's already an output port, but we don't have to declare the status. It's just going to do the toggle once we apply the once we apply our PWM. Okay, so now this is enough. Then the next thing we do is we just going to now look at what is now our void loop. So our void loop function, which is void loop function, what is expected to happen in the void loop function? So in the void loop, what we can do now is that we're going to try to use the digital val. Remember our digital val, which we've already made as a float. We're going to try to read a value from the analog read. Remember that for reading the value from the analog pin, we use the analog read. So the analog read is reading from the analog pin, right? Analog pin. So we are reading the value from the analog pin, and that value is a value that lies between 0 and 1023, right? It's a value that lies between 0 and 1023. So now we're reading the analog value, we're reading the digital representation of whatever is voltage that is presented to the analog port. We are taking that value to the digital val. So, and then that digital value representation of the analog voltage that has presented itself, it's a digital value that lies between 0 and 1023, right? That's what it is. And so now, but then this value is not compatible for PWM. PWM needs values that lie between 0 and 255. So what we do here now, we're going to say that duty cycle is equal to, now we're going to get the duty cycle value, which we have equally declared there, is going to be equal to the map. We are mapping our digital val, which is a value that lies between 0 and 1023. We are mapping it to a value that, okay, let me just delete this a bit, all right, so that I create more space. So let's say that what we are saying, what are we saying? We're saying that our duty cycle is equal to the map function. What is it mapping? It's mapping digital val, and this digital value, it's a value that lies between 0 and 1023. Yeah? We are mapping it to a value that should lie between 0 and 255. In other words, now the digital value will be a value that will be scaled from a value that lies between 0 and 1023 to a value that lies between 0 and 255. And now we have our duty cycle, which is really mapped, which is a value that lies between 0 and 255 using the map function. Now from the map function, now we could actually say that we can now use our analog write. Now the analog write would take the duty cycle and we'll output that duty cycle to pin number 3. That is Simple as all that. And this is the code that we're looking for. And in this case now, what we expect, we actually expect that now these values, are really in tandem. So we expect that pin number 3 should be outputting voltages that actually look like this, and this is very good, right? And so we can, and now depending on what value of analog that we're reading, this guy can shrink, can expand, and this is a technique that we've been talking about, and this is exactly what is going to happen. Now real quickly, let me just show you how it looks like in code. Just a minute. And so this is exactly what I've done right here, just maybe reduce on the timing here. Yeah, so we can see now it's not difficult to see. So what I've done here, in fact, I made not 1023, but I made 1023 right here, right? So what we're simply doing right here is that what I did was, in this case, actually I'm supposed to show you, but no big deal here. So what we've done, in this case, I was using a demo as a motor pin, but I've changed it to an LED, so that's no big deal. So I just say, okay, so we can say in this case, we can call this as our PWM pin in this case. And then our analog pin is that, our float digital value is that, and our duty cycle is that. And then we are saying that our PWM pin, is the output, which is pin number 3, as one of the pins that does analog to digital conversion, and that's it. It's an output put. And in the void loop, what we're simply doing is that we're getting the digital value and we're reading the value from the analog pin, and that is what we're doing. And then at the same time, again, we're saying that the duty cycle, which is really this guy right here, we're saying this is a guy that, of course, when we read, is going to lie between 0 and 1023. We don't want that. But what we want is that we want a value that lies between 0 and 255. So thanks to the map function, that may take the digital value, in this case, that lies between 0 and 1023 and map it between 0 and 255. And now since we have that value, now we can analog write to the duty cycle, we can analog write to the PWM pin. That's it. And so from here now, what we can simply do is that we can just sketch, refine, and compile. So it's time to compile. And now you can see how easy it is with the Arduino to do these PWM things. It's really something that is very easy. If we were to do all of this in at Megathon 2, of course, we will have to go through pins to try to do the configuration of this. But just right now, I just want to show you that we can. Of course, you can see it's done compiling, and we can just take a look. I think I did something somewhere where I wanted to show you so that I don't waste time on something that is easy like this one. So I have my PWM demo right here. So as it is trying to load, you can take a look at this and try to make out yourself what is really being talked about right here. So now you can see what we have. This is exactly the setup that we have, and we can try to center this one up here, right here. Okay, so now we can see here, this is pin number 3, this is A0, this is analog converter, and then we can also just try to, maybe for the sake of it, try to check out the virtual instrument. Maybe let's try to put an oscilloscope there and then just try to visualize what we can be getting from this. Now, I must confess that sometimes this may not really show very well, but it should be able to show some pulses that are coming through pin number 3 to the LED. Of course, the LED is expected to be blinking because it's blinking on and off depending on the value that we are reading from this guy right here. But of course, we can also try to load the hex file, and I'll try to visualize this. Well, what did I call this? Did I call it exam or something? All right, so we can try to check this one out and load the hex file, and and at some point we may just try to visualize certain things and then see what really happened and what is really happening. Of course, this guy doesn't show any data right here, but if we try to maybe lift this one up, I'm expecting that I should be able to see some data coming through the LED to start blinking. What is going on? It's crazy sometimes how this Proteus may, especially my Proteus, is not really in a good shape now, but all right, believe you me, when I tested it earlier, it was working just fine. I don't know, it could be okay. So so it was actually taking its time, trying to, sometimes just processes and stuff, right? But you can see here that really we're getting some sort of data, and if you check right on top right here, yeah, so this guy is trying to work, right? And you can see it's actually just blinking base. But then I want you to visualize this. I just don't know how I can make this one bigger, right? This is some data that we're seeing here, and if you see those things, these are pulses, right? And these are pulses, and I'm trying to see if I can get them to be a bit bigger, right? You can see here that's a pulse rate. So those are pulses, and so that makes it a bit, yeah. So we can maybe scroll the pulses around, right? So we can see that we're achieving some pulses. Okay, that makes it a bit where are they? Okay, so how do we make them now shrink? Yeah, guys, you need to play around with the oscilloscope in Proteus. It's kind of messy, right? But then now you can see here that we're actually getting some data, and these are the pulses that we're looking for, and you can try to play around with this to see if you can make some resolutions. Just trying to see if I can get a lot of them at once. Okay, so this is just for making heights, and this is for also doing that. What about this one? This one is for the same. I was just doing this right now. Okay, so we can actually make them okay, so let's see. Okay, but then now you pick the concept, right? You do, right? This is basically what we are. It's like kind of mess. I haven't used it in a long time, but you can do your thing. Okay, of course you can see that there are actually several passes that we're getting at the pin, as the pin is actually trying to toggle and switch on and off. Is this technique that if you were to apply it in real life, Now use prime width modulation technique, and we can see that for sure we're able to achieve the this prime width. But I also want to mention here, it's just kind of difficult to really see how we're changing the duty cycles here, because it's difficult to visualize it. But if you can see here, really, what I was expecting, depending on the resolution, I really can't see a good resolution. I wanted to be seeing that the duty cycle becomes bigger and small depending on this juggling that we're doing right here. It seems kind of messy a little bit, but it needs a bit of some cleanup. I guess it's possible to do the final cleanup, but you should be able to see that at different duty cycle, 50%, you should see a bigger square waveform, or something like that. And if you but then now it's kind of messed up a bit, but you can see that for sure we are actually receiving pulses through the pins. Okay, now guys, I'd like to thank you so much for viewing. This is really a simple example setup. There's no big deal about this PWM thing. It's especially that the way it's actually implemented in Arduino. In Ultimate 2, it would be a bit more complex. You remember that we have to set up the COM bits. We have to set up what type of PWM are we doing? Are we doing fast PWM? Or are we doing the other types of PWM? And then we have to go to great pains to look at the TCCROs, and we have to look at especially the TCCROs, and we have to look at how we set the clock bits and all of that. But then now here in Arduino, just use the analog write command, which is a command that is used to do the prime width modulation, and it takes the duty cycle plus the pin, and that's it. You're able to toggle the pin at different duty cycles that you're looking for. Okay, so for now, let's just call it quits, and would like to thank you for viewing, and I would like to wrap up. Thank you.